industry, whatever your specific industry ends up being, you're going to need to learn that code and standard, not by heart, but be very, very familiar with it. So I'm not going to go into too in-depth crazy details. And the point of this should not be afterwards that you guys come out and say, I know exactly what this code and standard or what clause number there is. That's not the purpose of this. The purpose of this is to inform you about the general structure of these codes and standards and how they can help you build the best types of welding procedures moving forward into your careers. So we're going to start off by giving just a breakdown of what we're going to focus on today. I'm going to essentially talk in general about 3 different main industry types. So pipeline being one, plant and facility being another one, and then finally the structural. And that's where I live, is within the structural field. So that's where my expertise lies. I'm decently familiar with the pipeline and plant and facility codes and standards, but I'm by no means an expert. So if you have questions, I will try my best to answer them. If you type something in the chat, I have it up on my other screen here. I will try to look at it and answer you as it's typed in there. And if I can't get you an answer, I will find somebody who can give you an appropriate answer for those codes. But it sounds like if you're having an ASME expert come in, he might be a better guy to give you the specific details or answers to plant and facility type questions, at least. And then finally, at the end, we have a work through example where we're actually going to work through and build a welding procedure. And I have a sample welding procedure to give to you guys at the end that you'll be able to see how we actually applied the code in order to build that. So the technical definition of a standard is essentially technical definitions and guidelines that allow everybody involved in the project or the production facility to carry out their tasks, right? So whether it's welders, inspectors, operators, anything like that, that's what a standard, it details all of those guidelines in there. Now, the difference between a standard and a code is wishy-washy. This is one of the definitions, but essentially a code is a standard that has been adopted by a government body and is therefore enforceable by law. So most of the ones that you'll see today are enforceable by law. If you're adopting that standard and you're having that certification to that standard, people can come after you and say, hey, look, were you following this properly? So that's pretty much the difference. But the larger difference that I want to highlight today is the difference between standards and specifications. Specifications is something that you will surely encounter, particularly in Alberta, if you end up working anywhere near the oil sands or touching it remotely, is specifications are these above and beyond standards. So essentially, they're made by companies or sometimes by overall industries, but by private interest groups, where there are additional considerations above and beyond the level of the standard. And essentially, all of these things serve to give clients a sense of accountability for their end user, for the person doing the fabrication. So it's essentially a quality standard that they can hold you to. So if you are given a project and you have a specification and a standard listed for it, this is now an agreed upon thing between both parties that says, this is exactly what you've agreed to do. This is exactly how you've agreed to fabricate it. And it holds you to a certain quality standard and also ensures that you have the proper certifications in place in order to be qualified for that code in the first place. Throughout all these different industries, there are different governing bodies that you'll hear bandied about, governing bodies like ASME, or you'll hear in Alberta ABSA or CWB, AWS. All of these are different governing bodies, but they have a very, very wide range of involvement. And that range of involvement really changes the way that you approach the application of those different codes. So in certain codes, you'll have people that are overly involved, or at least that's the prevailing opinion, is that they're overly involved. And people complain about them and say, oh, all these bureaucrats are slowing everything down. We have to get this approval and this approval. But there's a good and bad side to all these situations. If you have all those governing bodies being really, really hands-on and being really involved in the process, yes, it can slow things down, but it also provides that level of protection. When you're an engineer in particular and you're producing things to a code or standard and you don't have that governing body giving you that extra set of eyes and giving you that extra set of essentially confirmation that you've done stuff right and you're following the code appropriately, that onus is now all on you, right? So there's a lot of liability and risk that is also carried when governing bodies aren't very involved. So it's just something to consider in the background there as you move forward through your careers. You will need to consider that as a very real possibility. So now we're going to break down, I'm just going to break down some of the relevant codes for each of the different sectors, give them to you, not going to go into too much detail here, and then we'll start breaking down the individual sectors one by one. So the first one up here is pipelines. Z662 is the one that you'll hear all the time in Alberta. I'm guaranteeing that if you end up working at pipelines, you'll see every single specification that's ever been made thrown at you as well. But Z662 is your baseline. So this is a mandated thing across all of Canada. If you're going to build a pipeline that fits under their criteria for a pipeline, you're going to have to follow that. And it's mandated by the National Energy Board, which I've nicely not capitalized the N on. And this was done during the Pipeline Act. And essentially what they did is they said, this is a mandatory thing that you must follow. You must carry this certification and you must meet the requirements of Z662. So that's all pipelines across the board in Canada. The ones that I've listed down here at the bottom are just some additional ones that you'll run into. The first one, I believe, covers seamless pipe. The next one is fittings. The one after that, I believe, is flanges, and then valves. I'm not 100% sure on those. That's what those codes correspond to. Like I said, I'm not a pipeline engineer, but I believe that's what those correspond to. And essentially, those give additional information about those specific areas and how you would apply those things as well, beyond the requirements of Z662. And you'll see that kind of trend continue out throughout the rest of the industries here. When you go into plants and facilities, CSA B51 is this overarching one that kind of provides the safety and safety considerations behind it, but that's not really the ones you're going to hear as much or as relevant brought up when you're talking about plant and facility ones. Really, the ones that you'll hear in Alberta are ASME Section 9, and I'm sure that if you're having an ASME code expert talk, the next slide coming up here is going to look all too familiar after Thursday's lecture. And then the other ones that are there are the specific ones that go above and beyond what ASME main code says, like ASME B31.1 and B31.3 are ones that you hear talked about quite a bit, just in terms of going more specific for pressure piping. And just a quick note here is to note the difference between pressure piping and pipelines, not the same thing. Even though pipelines do operate under pressure, otherwise they would be very ineffective at their jobs. We're not the same thing as pressure piping, and those definitions are given within these codes. And then at the bottom, I've listed some of these API codes here. The API is the Pipeline Institute, the American Pipeline Institute, and essentially those codes there not only list, I believe the first one is for pressure vessels, but then the other three are for inspectors and the inspection qualifications for pressure vessels. So those are just, again, relevant ones you'll probably hear when you go into industry if you end up in that industry. As for the ASME codes, there's a lot of them out there. The one that we will focus on pretty much entirely when we talk about plants and facilities is the ASME Section 9. You'll hear that thrown around a lot within pressure vessel talk all the time. That is the one that covers all of the welding considerations for pressure vessels. So whether it be certification of welding individuals, welding personnel, sorry, or it's the actual qualification of your welding procedures, that's the one that's going to be relevant. And then again, like I mentioned, you have the B31.1 and B31.3 that you're talked about for power piping versus process piping. And again, those definitions are very clearly given within there on how those are distinguished from between the two. Don't work in the industry, not ultra familiar myself with what the actual difference is. So apologies for that. And then finally, the one that I am very familiar with is the structural industry. Within Canada, we live in this nice little limbo state where we very often, like all things, we end up with a Canadian version of things, and then we also have to end up abiding by the American version of things as well. So we live in this nice little limbo state. But the ones you'll hear talked about there, and we'll go into a lot more detail into this when we talk about the structural specifically, is W47.1 and W59, which are both administered by the Canadian Welding Bureau, which is a term you'll hear probably a lot if you stay involved in welding in any way. And those are both CSA, so Canadian Standards Association codes. And then the other ones that are going to be relevant here are S16, which is design of steel structures. So if you're building a building anywhere in Canada, that has all the design and limit states that you need to consider when you're doing that. And much more in a structural engineering vein than it is into a materials or welding side. And then there's the S6 code, which is the bridge code for bridge design. Now, I mentioned that we also have to abide by sometimes the American code. So AWS D11 lives there. AWS D11 is essentially equivalent to W47.1 plus W59. W47.1 covers the certification aspects of your company. So do you get your welder certified? How do you get your welding engineer certified, your welding supervisors, your actual company certified? Whereas W59 covers the application. All of that is covered in one code in D11. And actually, if we're being entirely honest, the Canadian code is at its basis was a direct copy of the American code. They just took the American code and they put it into a Canadian code to say that they could have a Canadian one. Since then, it's come a long way, and the Canadian code is, in my opinion, in a lot of ways, stepped past the American code in very positive ways. But that's the reality of it. So the nice thing is that they both speak the same language when we talk welding symbols and everything else. AWS D1.5 is the bridge welding code from the States, and it has AASHTO in there, which is the American Highway Association. They've also been involved in writing this code. And this is sort of the gold standard of bridge design or bridge welding. And so when we build bridges in Alberta, we actually don't just operate to S6, we have to operate to D1.5. And that's pretty unique in Canada. Nowhere else in Canada do they really employ D1.5 because it's considered a little bit above and beyond. But in Alberta, not only do they apply that code, they also have their own specifications that build off of it. And then the last one that's relevant here is AWS D1.8. And we use this not only when we do projects in the Pacific Northwest, which is just a seismic zone, but also in Vancouver, which is also subject to some of these seismic considerations. And essentially, there is no equivalent within the Canadian code of this. I mean, generally there is. They do have some supplements. But AWS D1.8 is really that, again, gold standard of seismic code and how you're supposed to apply it and all the factors that go into that. So that's sort of the brief overview of the different relevant codes you might hear bandied about within those industries. And we're going to go into a little more detail on each one of these industries now. Oh, right, I have some definitions first. Good for me for knowing my presentation. Weld procedure specifications. This is a term that I'm going to throw out a lot within this presentation, was shortened to WPS. And essentially what a WPS is a WPS is your recipe book. So essentially, when you go to do a weld procedure, it has to be written down somewhere so that people know what to do. And that piece of paper, that recipe that has all the welding parameters, what process you're using, what base materials it's good for, what filler material you're using, everything like that, all of that is going to be written on a single sheet, or certain codes, a couple sheets of paper. And that is your weld procedure. This is the recipe you can hand to the welder on the floor, and then he can go and make that weld. And that definition is pretty true throughout all of the codes. There's some variation. Unfortunately, because people love acronyms in engineering in general, WPS, well, it does mean the same thing for structural, isn't actually called the same thing. So when you hear me, you might hear me slip in a D into the middle of the word there and say WPDS. That's because within the structural industry, we have welding procedure data sheets, which are that recipe. And then WPS actually means something different, just to be extra confusing. And you'll see that throughout the presentation here is there's a lot of things that have the exact same terminology behind them and mean a completely different thing if you're in a different industry or referencing a different code, which is unfortunate, but it's the realities of engineering. And then the last thing I wanted to talk about here is weld procedure pre-qualification. So this is a term you might hear as pre-qualified welding procedures. And what that means is essentially that they have enough data collected, enough experiments have been run that they're, with a large degree of confidence, they're able to say that if you follow this reasonable range of parameters and you're doing this joint and all these different aspects, we're going to say that's pre-qualified. You don't have to do any testing. You don't have to prove anything to us. We have enough data to say that you really can't screw that up. So what you can do with a pre-qualified welding procedure is essentially have a cookie cutter recipe. So a recipe where you just have to essentially print it out. You may have to still send it in for approval from either a company or from a governing body, but more or less that recipe is good to go. If that doesn't apply, which it very often doesn't, particularly in Alberta, you need to then support your welding procedure or certify your welding procedure through what's called a procedure qualification record, or PQR. I know, more acronyms. And a PQR essentially serves as the testing that proves out your welding procedure. And the requirements of testing for a given welding procedure are also going to be listed within the code. And we'll go through and within our example that we're going to run through today, that will be mentioned. But essentially, PQRs support non-pre-qualified welding procedures, which then can be passed along to the floor. And I've organized a little flow chart here. This is taken a little bit touched up from a really good reference material on weld procedure development. But essentially, this is the basic steps that you take in order to build a welding procedure. So when you first start off with a welding procedure, you need to start off by determining what code are you operating on. So are you building a pipeline? Well, it's probably Z662. Is there any specifications that apply? Now you need to determine all those things. The next step in the process is determining the range of your weld procedure. So you need to figure out, what do you want your welding procedure to do? So let's take the instance of building a pipeline. Is it going to be only good for 36-inch pipe, or is it going to be good for 36 and 24-inch pipe? Is it going to be an automated welding procedure? Is it going to be done with MIG? Is it going to be done with stick? All those different things need to be determined. So you need to figure out exactly what you want your welding procedure to do. And in this is a big consideration, and we'll talk about this more as we go, but essentially there's this big consideration of, do you want your welding procedure to be built to future-proof it? Do you want it to be built in such a way that you don't have to go back and requalify it a million times to get a bunch of different welding procedures, right? So you want to hit what I would like to call the Goldilocks zone, where you don't want to have a welding procedure that is so specific that in order to do a job, you need to have 40 welding procedures when 5 welding procedures with a sufficient range would do. But you also don't want to open up the welding procedure range so massively that if you hand it to a guy on the floor, he has so much freedom and flexibility that he doesn't really know what he's doing, and he's going to actually cause damage by not being given that specificity. So you have to play it, both those factors. And to the largest point is just to avoid the cost of these things. Very often a PQR can cost, like one PQR could cost you about, I don't know, given anywhere from like $1,000 up to like $10,000 for a given PQR, depending on how it goes throughout the process. So there's a large amount of cost associated with this. So you want to minimize that cost. And the other problem is when, especially when you're dealing with governing bodies, the process and the timeline for that takes an extraordinarily long time, sometimes up to 2 months in order to get a procedure qualified. So if you're having to go back and touch these things up and you don't have a good understanding of what your range is, then you're going to cost your company time and money as it moves forward. So once you've determined that range, then you can determine based on your code whether or not you need to do testing. So is it pre-qualified or not? If you have to do testing, then you have to get all the other steps in the row. So you have to select all your materials, figure out your process, get the actual testing done, record all the parameters, get the non-destructive and destructive testing done, write up that PQR. Then you have to write the weld procedure based on the results of your PQR and then submit it to approval. And that approval can be to the client or it could be to a governing body. So there's a lot of different steps in that process. And one of the reasons why people like pre-qualified procedures where they can is they essentially get to jump from that, determine the WPDS range, to submitting for approval. It's a really nice step, but it doesn't always work, particularly given certain industries. All right, so first up, we're going to jump into pipeline welding procedures. And yes, that is a good note. I saw that in the chat. He or she is a very good note. Pardon my generalization there. So when we talk pipeline welding procedures, like I said, essentially that's covered off in Z662. Now, this is one of these instances where there is no pre-qualified welding procedures. For pipelines, you have to do a PQR every single time. Now, granted, you can do a PQR, you can create a welding procedure, and that may be good for future projects, which is where we want to build that future proofing, but not always. And certain companies will just require you to build a PQR every single time you go to a new project. So you have to have that in the back of your mind. You're going into this knowing you're going to do testing. Typically, these are not going to be reviewed by a governing body. So the governing body in this case is the National Energy Board. They may audit it. If you're working for a huge pipeline, like when Enbridge builds pipelines, they're probably going to take a look and audit those welding procedures. Besides that, it's going to probably be reviewed by the contractor, so that would be your company, and by the owner, so the client at the end of the day, be that a government client or be that a private client. And it is going to be reviewed and subject to approval. But that means that that onus really is being taken on by the engineer preparing that welding procedure throughout. So I'm going to chuck some of these things in here. Like I said, there's no need to memorize all these clauses. If you get into this industry, you're going to become more than familiar with these things. Materials for Z662 are shown in clause 5, specifically that table, and they cover the pipelines and all the components here. One of the things that I did want to highlight, and this is one of these confusing things that has different definitions depending on the code, is notch toughness. So notch toughness, we live in Alberta, and in the winter, particularly If you're welding or doing anything up north, the temperatures are very, very low. So typically the general temperature that's considered for active service is minus 45, and sometimes it goes as low as minus 60. But essentially, we're operating in a very, very cold weather climate, which means that you need to make sure that whatever you're doing for welding, it is going to carry through and not fail when you actually put it into the field. So I'm sure you guys, from what Patricia said, have gone through a little bit of the NDE side and maybe testing. And if you're a materials engineer, you surely will have heard of Sharpie V-notch testing. Maybe the MatEs too in MatE 202, but Sharpie V-notch testing is essentially measuring the impact properties or the toughness of the steel. And unfortunately, notch toughness is the way that we measure this throughout any welding code, but that notch toughness definition is completely different from one code to another. So here they're organized by categories, and you'll hear category language throughout the rest of the codes as well, but it doesn't necessarily actually apply because the categories are completely organized differently. So within the pipeline field, essentially, category 1 is something where you don't need to care about your impact properties. Category 2 is you care about the impact properties. And not only that, when you do an impact test, you actually have to look at the fracture surfaces to see how that failure occurred, right? So did it bust through and the crack propagated most of the way, or did the impact actually do most of the damage? They start to care about that in category 2. Category 3 is realistically what, if you're going to have notch toughness requirements, what most of it will fall into. And that really, they don't care about the fracture appearance. They care about how much energy did it take to break that piece, right? But like I said, one thing to note about notch toughness and categories is completely different code to code. In terms of the variables that go into building a welding procedure considered by Z662, they have that all contained in clause 7. And this will be very, very similar list of variables, no matter what field you're in or no matter what code you're referencing. So they're going to care about what welding process you've chosen, what the joint geometry is. So is it a V? Is it a fillet weld? What does that joint geometry look like? They're going to care what the base material is, what you're using as a filler material. So fluxes would be counted into that for subarc. Shielding gas definitely matters. The position, direction of welding. So is it vertical uphand or downhand is where direction really becomes relevant. Doesn't really become relevant any other direction, anything else besides the pipelines and then vertical up, vertical down. Preheat and interpass they're going to care about, and then post-weld heat treat as well. And then the main welding parameters that you guys will have learned throughout the class. So amperage, voltage, travel speed, stick out, all those different things will all be included as well in terms of variables to be considered. And then there's also the technique, right? So are you welding in stringer bead? So stringer bead is just a single bead. You're not doing anything fancy. You're just running it straight across. Or are you putting in a weave, right? Are you trying to build a bigger thing? How much is your layer size varying? All those things are considered in that technique. So that's just kind of the blast of all the different variables that go into building welding procedures. And it's specific here to pipelines, but these same lists apply to all of the different industries. Another term that you're going to hear, and it goes through all the codes, is essential variables. So for essential variables, what these means is all of these variables here, certain ones considered within there are considered essential, which means that if you change those variables outside of the given limits, and all the codes will state, and we'll see here in a second what those essential variables are. If you change your parameters, or you want to change the parameters in your welding procedure outside of those given limits, you are going to have to perform a new PQR. So what that essentially entails is you want to be very, very careful. And when we're doing that sort of future proofing and planning of our welding procedure and determining the range, the essential variables are really what you want to consider, because that's what's going to affect whether or not you need to do a new PQR. So if you change your amperage by 10 amps at the bottom end, nobody's probably going to care. And it probably won't be listed on the essential variables. I mean, it could be for given codes, but it probably will not matter. But if you want to, instead of weld on a 350W steel, you want to now weld on stainless steel, people are going to care. And they're going to require you to do a new PQR. So you want to future-proof it as best you can. And certain times you can't get away from it. If you're changing base materials entirely, you're not going to build a weld procedure that's good for two completely different families of base material. but to the best of your ability, you should be planning with those essential variables. So I've essentially straight copy pasted out of Z662 the table 7.3 that lists all of the essential variables. I'm not going to go through this at all. I'm just going to show it to you and have it as a example in here. The essential variables are going to look different for all the different codes. But basically, the big takeaway that I want to give here is that it's clearly defined what variables and parameters are subject to these limitations, and you need to become familiar with. So in the pipeline code, it's organized by the diameter, outer diameter of the pipe, as well as if you're using automated welding or not. Pardon me, I'm just gonna take a drink. And then the actual variable is shown on the left-hand sides here. So I've put, like I said, the entire table in here. I'm not gonna go through it. You can look through it on your own time if you're interested. But I just want to give you that framework or example to have to base that off of. So the next thing up here that I wanted to highlight out of this code is the PQR testing. So one of the interesting things about pipelines is that, like I said, the welding procedures are always subject to these PQRs. So you always have to do testing. Now, the nice thing is it's very clearly defined what kind of testing you have to do. So what they have is essentially given the size of your pipe, they will tell you which tests you need to do. So all the tests are listed here, and then they'll tell you how many of those tests you need to do for each one, right? So for smaller pipes, you don't need to do as many structural tests, but the larger you get, the more they're going to expect that baseline standard to be there. So not only are they going to tell you, what tests you need to do, they're also going to tell you where you're going to need to extract those samples from. So given your different size of pipe here shown, they're going to tell you exactly where to extract all of these different types of samples. So if you're doing this small size of pipe here, this less than 60 mil outer diameter, you're going to have to extract nick break and root bend samples from these exact locations within your sample, right? So you need to have everything very, very well documented and prove to a client at the end of the day that you extracted those samples from where you said you were going to, right? So all of that is clearly defined in the code, but it shows you exactly what you need to do. The types of tests themselves, I'm sure you guys will have seen some of these tests before. Tension testing is one of them that's listed. Tensile test is exactly what you've seen and heard of, especially if I think all of you will have gone through MatE 202. If you haven't, then feel free to flag me down and ask a question about it specifically. But tension testing, essentially, you're going to do your weld. Your weld should be situated for Z662 right in the middle of your plate. And then you're going to put it within the sample dimensions. You're going to put it into a tensile testing machine and you're going to pull it. And essentially, they care not only about the number, but they also want to look at that fracture surface and see where it failed, right? They're looking for failures within the heat affected zone, different places of where that weld could have failed. And it can reveal a lot about the integrity of a weld based on where it failed. So tension testing is one that was mentioned. Nick break testing, and this is a very, very specific one to pipelines. I don't really know that you'll see it too many other places, but essentially you prepare your sample, and your sample is more or less this rectangular prism with a weld in the middle of it, and then you're going to notch it on both sides. So you machine it down and you notch it. And these can be cut by a hacksaw. There are other methods of cutting it. And then essentially you fracture it by applying a load, probably a press. Doesn't have to be, but that's the easiest way to do this. And then really what they care about for a nick break test is examining what that fracture surface looks like, right? Did the failure happen more to one side than the other? How much of that weld material is left over? Did it break somewhere else that wasn't in the weld? All of those things start to matter. And all of those parameters and acceptance criteria are clearly listed within the code. You have root and face bend specimens. So root bending. So essentially when you have a bend specimen, I think I included a picture here. So essentially bend specimens end up looking like these U-shaped horseshoes where you're essentially just applying a load in the middle and it's got two brace points at the either side end of the piece. Oh, flying all over the place here. So you're going to apply a load in the middle here, and then you're going to have brace points at the end, and you're bending it you see what happens to that weld. So if it's a root bend specimen, you're going to bend about the root of the weld. If it's face bend, you're going to bend about this point. If it's a side bend, you're actually going to cut the sample a little bit thinner and cut and bend about that side axis there. And what you get is these samples here at the end of the day. And what they want to see out of this is a couple of things. They're looking to see, first of all, did that weld have the strength and ductility to allow the bend? So did it bend or did it just break? If it breaks, you're going to fail the test. But there's acceptance criteria. So I very, very often within these tests, you'll see small little micro cracks at the develop, especially in the heat affected zone or at the weld's root. Some of those cracks could be acceptable. The acceptance criteria is all listed within the code, but some of them are going to be unacceptable. Or if you bend it and porosity starts to show up that you didn't see when the sample was just cut, all those things is what they're looking for to give it a pass-fail criteria. And you'll see these tests like side and root bends throughout all the codes. Like I said, nick break is a little bit specific to pipeline, but you'll see these types of tests throughout all of the different codes. So yeah, that's kind of your drive-by view of pipeline weld procedures. I know it's quick, but that's what the main highlights I wanted to pull. Of course, there's lessons to be learned throughout all of them, and there's commonalities to be learned throughout all of them. So hopefully, if you have any questions, just chuck them in the chat, and I'll try to answer them as best I can. But really, this is going to be very, very drive-by. Plant and facility welding procedures. Like I said, you're going to get much more information about this, so I'm not going to go into too much detail into this area. But mainly what we're going to focus on is ASME Section 9. And ASME Section 9 covers the qualification for all the welding procedures, welders themselves and the operators and all those different aspects of it. And then there's sometimes additional requirements that will creep in from these other ASME codes. In this particular industry, there are pre-qualified welding procedures, but from my experience and interacting with people within the field, it's really not a reality that you can apply pre-qualified welding procedures. For the most part, you're looking at doing PQRs. And this is one of these very, very unique things in Alberta where there's one of these governing bodies that gets a lot of flack. When you go to submit these welding procedures, you not only have to get the approval from the owner or the client, but you also need to get it from ABSA. And this is the Boiler Safety Association. And essentially, their job is, as a governing body, to ensure that you are adhering to the code very, very strictly. And like I said, there's good and bad aspects to this relationship, but ABSA in particular is very, very well known for being very, very hands-on and very, very in the process. So you'll hear engineers complaining about it. I'm sure that if you go to work in the field, you might complain about it. But the reality is that there's nothing that they're doing that is wrong. They are ensuring that the code is properly applied. And even though they may slow down certain operations or cost people money, I think in a lot of ways, having that second set of eyes and making sure things are adhered to is really a good thing. And it also saves a lot of liability at the end of the day. But yeah, if you work within this field, you'll definitely hear about ABSA. So the part in particular of ASME Section 9 that we're going to look at is this QW or welding. There's 5 articles within it, so 5 different sections within it. And you'll see that the ASME code, if you ever flip through it, if you want to do casual reading, I'm guessing not, but if you end up working in the field, you'll see that that's written a little bit differently than some of the other codes. And it's very, very self-referential. So different, as you go through the code, you'll see that there's a lot of like, okay, see this clause, now see this clause. It's one of those codes where you do a lot of bouncing around, and that's true of all codes in general. But ASME Section 9 in particular is very, very sticky about those types of things. So we have the 5 different articles here we're going to run through. So the first one is sort of the welding requirements. So this is more general requirements. So it's going to give you information about the basic welding procedures, some of the basic testing requirements, nothing too insane. This is sort of just your general introduction within Article 1. Article 2 is where we get into actual weld procedure qualification. So in this section, they actually list all of your essential variables, something they call supplementary essential variables, which we'll get into, which is another confusing thing, and then non-essential variables, which is anything that doesn't fall into those first 2 categories. And then one of the other things that's very unique to this code is they talk about tempered bead welding. So using, I don't know if you guys have talked about this in class or not, but essentially using the current pass to affect the metallurgical constitution of previous passes. So you can affect essentially the properties of the previous passes by welding over it again and subjecting it to another heat cycle. So you can do that. Typically it's done to give hard phases a little bit more ductility or provide them with a different level of toughness. But it's very, very well explained, but it's not one of the codes. It's pretty much one of the only codes that actually talks about temper bead welding. In other codes, it's maybe referred to, but there's no explanation given towards it. So essential variables here, much the same as what we saw in the pipeline code. They're listed there. They're very clearly listed, but they have this new term that they throw in there called supplementary essential variables. But essentially the only supplementary essential variable is this notch toughness requirement. So for low temperature, do they require you to have a CVN, a sharp UV notch test that's passed? I don't know why they call it supplementary essential variables and not just notch toughness requirement. Seems confusing to me, or just include it within the essential variables, but it's all within there. And then they also list the non-essential variables as well. In that section as well, and this is just to highlight one of the interesting things about ASME section 9 is they list all the applicable welding processes, which if you have a look at this list, you'd be hard pressed to find a welding process that isn't listed here. There's a couple, but it's pretty all inclusive. And the reason that they do that is to cover all their bases, to make sure that essentially nobody can surprise them as they go through. But yeah, there's good coverage of pretty much any single welding process where other codes are not this widespread. Welding performance qualifications are within there. So this has the information regarding welder and welding operator qualification, tells you essentially what kind of testing is required to get them their initial qualification, how often they need to do retests, how long is their certification good for. All those aspects will be covered within that, as well as the coupons. Then next one up is welding data, and this is one of the important ones. This contains information about base material as well as filler material. And you'll hear these two things kind of thrown out, F numbers and P numbers. And I've included links to them here where they actually have websites that are just straight up the F and P numbers. So P numbers are essentially all of the base materials that you can use within ASME Section 9 are given a P number. So whether it's ferrous steels or nickel containing steels or manganese containing steels, whatever it is, that's going to have a separate P number. And that's all listed on that website there. But essentially the big takeaway out of this, and for the F numbers as well, which we'll see in a second, is when you're planning qualification for welding procedures, and not only welding procedures, but welders as well, whatever you test them with for base material gives you a certain qualification range. And so I brought that table out from ASME Section 9 here, right? So it's what was the base material chosen for the test, and what does that mean it's good for, right? So you want to be smart about this. So you want to choose a base material that at the end of the day will allow you to build in the most flexibility moving forward. So you want to have a base material that's going to give you the largest range at the end of the day, or maybe not the largest range, but the most useful range to you. F numbers are much the same, but they are for electrodes, so for your actual consumables here. And welders can be qualified to multiple categories, but again, same type of thing. You need to be smart about what you're selecting as the initial test so that you can build in that future proofing. And that's why F and P numbers are something good to become familiar with if you're working within those fields. I am not personally familiar with these. If you're working within these fields, though, they're very, very useful because they give you that ability to plan and to have that sort of future proofing built in as you go through qualifying welders and welding procedures. And then the last one here that is of relevance out of ASME Section 9 is the Article 5, which is standard weld procedures. This is not at all common in Alberta. No notch toughness applicability, so no low temperature. So good luck building a pressure vessel that isn't going to be subject to something with low temperature requirements. And the ironic thing is even though they call these standard welding procedures, they still need testing and test coupons. So I'm not really sure what the purpose of these are in Alberta. It's very, very interesting to list them all in there and to have that option available, but it sounds like it's not the most useful option. And maybe you'll get into a field or work in a company that will use them. So I just want to make it available to you that they are there, but I can't actually speak to them being very widely used whatsoever. So that was our plant and facility look. Yeah, that's a good point, Eddie. Yeah, Exactly that, which is trying to reduce the number of weld procedures, which is that future proofing, right? You don't want to have a bunch of welding procedures that are going to cost you a bunch of time and money or / confusion, right? If this is a little anecdotal, but when I first joined my company, they through acquisition and different things, they had gotten a bunch of welding procedures from all of their acquisitions throughout the years. And when I joined, we were looking at over 2,000 welding procedures, which is useless. It's completely extraordinary and exorbitant number, and it's completely useless. So you want to, at best, be working with a limited number of welding procedures so that, one, you can make sure that the appropriate one is given to the people on the floor, but also that the data within them is useful as well, right? So, okay, so now we're going to go to structural welding procedures. This is my bread and butter. So if you have questions here, I should hopefully be able to answer them. Otherwise, maybe I'm not so good at my job. We'll start off, again, we're focusing on the Canadian market. So we'll talk a little bit at the very, very end about the American codes, but we're only going to mention at the end once we've gone through the actual working example. So, or case study, I guess. The first thing was that I mentioned was W471. So W471 is sort of your certification code. So this covers the certification of welders, welding operators, welding supervisors, so the people who stare at the welders while they're welding. It covers off the certification of the companies themselves. So companies need to be certified through this code. Welding engineers need to be certified to this code. So I had to write tests to be able to attain my certification here. And this is entirely administered by the Canadian Welding Bureau. So the Canadian Welding Bureau is this agency that works to administer this code as well as doing some other auditing type operations. And W471 is purely for certification. So it gives you want to have Jimmy the welder or Jane the welder create a welding, get certified. You need to get the certification requirements out of W471 and have them complete the required tests that they need to be able to perform the processes that you want them to be able to. Within W471, there's 3 distinct divisions or levels of certification. The lowest on the totem pole is Division 3 companies. So Division 3 companies do not have any requirement to employ or retain a welding engineer. So this means that if they have welding procedures, they are using the cookie cutter. So they're using the pre-qualified welding procedures. They are submitting to them to the CWB to get approval. And the CWB actually will provide a CWB stamp on welding procedures that they're approving. And so Division 3 companies are typically very, very small. They'll do small work like just doing handrail or something like that. You're talking pretty small companies, not doing any large type of project. Division 2 companies, in a previous lifetime, I worked for a Division 2 company briefly, and those companies retain a welding engineer on a part-time basis. So they don't employ a welding engineer like myself full-time. They purely retain them and bring them in to write their welding procedures and perform audits on their welding operations to ensure that they meet the certification requirement. But essentially, it's a good methodology of getting these mid-sized companies a welding engineer and getting them to be able to have a level of certification with W471 without having the expense of a full-time welding engineer. And then Division 1 are companies like Supreme Steel, where you have to employ a welding engineer on a full-time basis in order to have that certification. And Division 1, the real reason that people go after Division 1 as a certification is to be able to seek out large work. So a company like mine, where we've been responsible for a number of very large construction projects. So if you're looking for stuff that we've done, any of the Anthony Henday bridges, we fabricated. A lot of skyscrapers in Seattle, we fabricated. Amazon spheres, we fabricated. Bow Tower in Calgary, all the Calgary bridge ring roads. All those types of things are things that we've fabricated. And the only reason that we're able to even qualify for those jobs is because we're a Division 1 company. So it's trusting that you have the in-house expertise to be able to adapt at any given time. You're not having to call a guy or a girl in and try to get them to make that last minute change and get everything to work properly. You have that person in-house who is going to perform that duty for you. Welding procedure specifications. So this is where we get into the weird thing where structural industry decided that they needed to be special. So welding procedure specifications do not mean the same thing. So welding procedures and all the other codes were called WPSs. WPSs in the structural industry, or at least in the Canadian structural industry, actually refer to overall guidelines for specific processes. So our company has a WPS for each one of the welding processes. So stick, GMA, metal core, flux core, subarc. We have all these WPSs for those. And essentially what it is a general guideline or general procedure. If you're going to apply that process, that's where you're going to go, is to look at that. The unfortunate part and the honest truth of it is that I've written up this welding procedure specification for all of the welding processes that we use as a company. And I think the document all in with all the welding processes is like a 90-page document, which includes all the required information, and it's approved and all these things. And I may be the only individual in my company who's ever read it. Welding procedure specifications are designed to be this reference point if welders are looking for help or if they want to get specificity on a process. But the reality is that nobody actually uses them in practice. They are completely a certification requirement. What people care about is that welding recipe. And in the Canadian Welding Code for structural, it's referred to as a WPDS, or welding procedure data sheet. So that's your actual recipe, like all the other codes, that contains all of the useful information that you could hand to a welder, and the welder could actually go and weld it. The welding procedure specification will not give them that ability. It's essentially just a general list. The idea being that the welding procedure data sheet will fit within the general range created by the WPS. But again, reality is nobody looks at WPS, which is sad because I put a lot of work into mine, but no, I don't think anybody's ever read it. Then you get into the next step here, which is that they distinguish between the certification code and the actual application code. So like I said, W47.1 is your certification code administered by the CWB, both are. And that's all about getting people qualified and getting companies qualified. W59 is the actual application. So that covers off workmanship, that covers off your actual welding procedure development. All of those things are covered off in W59, the actual application of the code. Neither code is useful without the other one. Essentially, they're completely based on one another, right? One is certification, one is implementation. One of the couple of things I wanted to highlight out of this, W59, all the welding symbols listed there conform to the AWS A2.4, which is a standard of the American Welding Society that covers off welding symbols, meaning that between Canada and the United States, at least, you have a uniformity in how we treat welding symbols. So all the definitions, with a couple of exceptions, are the same, meaning that you can work within both countries and not have an issue. When you go into other countries, and very often we have projects where a European designer has created the drawings for it and it comes to us, and we get the welding symbols in the European format, and those, when people first look at them, might as well be written in hieroglyphics because they're completely different. And everything means completely different things. A good example is fillet welds. Fillet welds in Canada, the US, we define the fillet weld size as the actual leg size. So if you have your corner joint here and you're putting a fillet weld across, we're talking about the actual leg size here when we talk about the size of a fillet weld. But in Europe, they talk about it as the throat size. So from this theoretical point where your weld peak, your weld reinforcement is at its highest point, down to the root is what the Europeans are referring to there. And it creates a lot of confusion. So being familiar with the welding symbols, the good news is if you're working within Canada and US, it's all uniform. If you work within Europe, it's completely different. In South America, I believe sometimes works within the European codes. So you get a lot of variability there. W59 covers off statically loaded structures, so structures that aren't being subjected to cyclic loading, or dynamically loaded ones where you're gonna have to consider fatigue and those types of things. One of the things that I wanted to mention here is you'll hear base materials, unlike P numbers that we saw in the last section, you'll hear them talked about in terms of groups. And essentially 95%, or probably close to like 98% of the materials that we weld with as a company are used in steel construction in general, all fall into what's known as this group 1, 2, 3. And it's sort of this bracketed area where it's widely accepted that those three groups are lumped together. So you'll see in the example welding procedure that I have generated for this case study, that's exactly what's listed there. And those welding procedures, that steel group is all kind of lumped in together. There is a lot of pre-qualified welding procedures in there. The real exception to pre-qualified procedures is if you're doing something that is outside of the norm, which would have to be pretty outside of the norm because pretty much every joint geometry you could dream up is covered off by a pre-qualified welding procedure. Unfortunately, because we live in Alberta, Notch toughness requirements are a large thing, and there's no pre-qualification if you have a notch toughness requirement. And the case study that we're going to do will highlight this. Welding symbols, I'm not going to go into that. I'm trusting that you guys have seen enough of that through Patricio, but just know that that is all listed within these codes as well. And it is required by the code to list all of that in the drawings. And everybody from the welders up should be familiar with reading them. Sometimes you get a little bit of variability there, but everybody should be familiar with how to read welding procedures and distinguish the different types. And then I've also listed in here some of the information out of here. This is sort of just an FYI. You'll often hear people talk about different welding positions. These are the ones that are considered by the structural industry. So you have your flat position, you have your, these are for fillet welds and these ones are for groove welds. So left-hand side fillet welds, right-hand side groove welds. And you have the 4 different weld positions, which is flat, horizontal, vertical, and overhead. And based on what you choose to qualify your procedure with, you can get a certain range of qualifications. So let's say I want to do a fillet and I want to be able to do a fillet in the flat position as well as the overhead position. Well, I don't need to do a test for flat and for overhead. I only need to do the test for overhead. And then based on the overhead, they're trusting that if I can do an overhead weld and pass it, I can also do a flat position weld. And this sort of same idea applies to welder qualifications as well as weld procedure qualifications. So it's again building in that thought process of when you design a procedure, you want to be as smart as you can and prevent yourself from having future work and future welding procedures or overloading yourself with welding procedures. So try to be as smart as you can when you're designing that. So last thing here up, and this, how are we doing for time? Okay, we're not doing too bad. Is I wanted to focus on a case study here, and a case study that's something I'm very familiar with, which is a bridge girder. So what I wanted to give you guys here is sort of a baseline scenario of how we would actually build a welding procedure. And at the end of the day, I will show you, so long as nothing goes wrong with this Zoom here, I will show you the welding procedure that is currently in use in our company. I've sort of taken out some of the more pertinent information, but the weld procedure that is currently in use within our company for fabrication of these bridge girders and sort of the process that we went through to qualify the procedure. So if you're not familiar with a bridge girder, I put some examples up here where we have 5 different girder lines shown here. And a bridge girder is essentially an I-beam, right? So you have a thick plate at the top that's pretty, not very wide, and then a thick plate at the bottom that's not very wide, and then you have a pretty thin plate that stretches between the two. And so these 2 thick plates at the top and bottom are called your flanges, and the plate in the middle is known as your web plate. And I put a nice little little PowerPoint drawn version of that so you can see it. But essentially what we're looking at today is how we would qualify this fillet weld. So when we build bridges, and we build bridge girders a lot at my company, when you're fixing these flanges to these webs, they're essentially affixed with 4 welds, 1 in each one of these corners. And these are all fillet welds. Now these girders, you saw in the picture here, this is a girder line. So it's actually made up of a couple different girder segments all spliced together. But these girders sections in and of themselves can stretch from 20 feet up to, I've seen girders that were like 40 meters long in and of themselves and had like a 3-meter depth. So essentially, I've seen some bridge girders that we fabricated that this web plate was about 3 meters in depth. So these things are absolutely massive. They have to close off roads to transport them. Really, really impressive stuff. But we deal with a very, very wide range of materials here. So when we build a welding procedure for these, we want to try and make the most useful welding procedure that we can. And actually the weld procedure that I'm going to show you today that we've designed has been in implementation since essentially a couple months after I started with the company. And we've used it without any issue on every single bridge project that's come through our company. So we built in a very, very versatile weld procedure and saved ourselves that cost each time, which I think this procedure in particular cost us about $8,000 to qualify, just the procedure. So the problem set here is that we're going to use this 350 AT Cat 3 material. So 350 AT, I'll explain what that means in a second, but it's a atmospheric steel with a yield strength of 350 megapascals. And then the Cat 3 here references this sort of notch toughness or low temperature requirement. We want to create a fillet weld that we're going to apply in the horizontal position. And we're going to remove what is typical for us is that we would have a D1.5 consideration here. So we'd have to make sure we're balancing both codes, but I'm going to remove that. And we're just going to focus on the Canadian code. And we're only going to focus on being compliant there. And then the flange material thickness we're going to choose here is 40 millimeters. That's sort of on the low end of flange thicknesses. Our flange thicknesses typically are in like the 60 millimeter range, sometimes going up to like 100 millimeters. And then 14 millimeter web material, which is pretty representative. It bounces anywhere between, you'll see 14 millimeter up to about 1 inch or 25 millimeter web material. So that's a problem. We want to design a welding procedure to cover off fillet welds for this material, this 350 AT Cat 3 material. We're meeting the Canadian structural requirements, and these are our thicknesses that we want to do. So we start building, we know we have to do low temperature, so we can't use pre-qualified welding procedures. We've already crossed that off the list. So now we know that, are we looking for, when we're looking to build our procedure qualification or PQR, we're going to look at, well, what process do we want to use? So when we're building these procedures, we want to typically be very, very efficient, or as efficient as we can be. So in this case, we're going to select sub-arc welding, because sub-arc welding can be run by a machine and it can be automated. You can literally stick a tractor into this joint and run it the entire length of this girder in one shot. And because sub-arc is such a large heat input and high deposition process, you're able to deposit your required weld in one pass. And one of the interesting things that's considered by the Canadian Welding Code is that because sub-arc is this type of process, you get an extra 2 millimeters. So if the typical weld size that's allowable in one pass for a fillet weld under most codes is 8 millimeters. So not independent of the actual process, 8 millimeters is the maximum weld size you can guarantee with one pass. Beyond that, you're not allowed to do a single pass that stretches larger than that. But for sub-arc, there's this exception where because sub-arc has this nice deep penetration characteristic from the high heat input and high amperage, you get to consider an extra 2 millimeters of penetration. So sub-arc is not only ideal because you can have it efficient, but it also gets this, if you have a 10 millimeter weld that's called out on a drawing, you can actually do that in one pass because you can downsize that by that 2 millimeters extra to an 8 mil weld. So sub-arc is the process we're going to use here, and that's pretty much universal of all bridge girders. So the test coupon, we're going to look within the specification and we're going to say, we want to have this notch tested. So can we use a test coupon that's a fillet weld? No, because if you went to go take a fillet weld and you went to go put that in a Sharpie, it just wouldn't work. You need a sort of rectangular prism shaped sample. So you need to extract that from a CJP weld or a complete joint penetration weld. Sometimes you can do it from PJPs, but you want to extract it from a full penetration weld. So you're going to create a groove weld with backing, and those requirements are going to be listed for what that plate looks like within the code. So we go to the appropriate drawing and we say, okay, we want to do some CVN testing for our project. And it's going to tell us exactly what the plate dimensions need to be, where all of those samples are going to be extracted, everything like that. So what they say in there is something interesting to point out, is they'll say, look, you need to do a minimum 300 millimeter plate. So you need to do a minimum of a 1 foot plate in length, and then the dimension is given on the side as well. But it is in your best interest when you're doing procedure qualifications, and this is independent of code, to do a slightly longer plate. And the reason for that is if you fail one of the tests within the plate dimensions that you've done here, certain codes, and certain codes won't allow you to do this, but certain codes in the structural Canadian codes will allow you to retest outside of that. They won't allow you to retest infinitely, but they will allow you one retest outside of that. So essentially, if you build your plate to say 400 millimeters in length and you fail one set of your CVN samples in here, let's say you fail your weld metal CVNs, so the ones that are being hit here, you can go to that outer 400, that outer 100 mil and extract new samples from that area, which sort of feels like cheating, but it's the realities of the code, and people build this in no matter where they are. Pipelines do it a lot. It's that whole idea of, well, I failed here, I'll just move over, which seems sort of like a broken system, and in a lot of ways it is a broken system, I won't lie to you, but because the system is broken, you would like to use it as best you can. Now, if you get really, really horrible results, probably don't move over and just try to use that, because very likely you're going to fail again. And also, do you really want to trust the integrity of that weld with your engineering stamp? Maybe not, right? So there's those considerations to take advantage of. But if it's really, really close and it fails, well, you can get out of a lot of expense of having to redo the entire test just by building a slightly longer plate. So we have our test coupon essentially defined now. We know what our plate looks like. So now we're going to choose our filler metal. So our filler metal, to match our base material here, our base material, like I mentioned, is a weathering steel. So what weathering steels are they're used for bridges. And if you remember back from that first picture I showed you, and I'll try to zoom up here, you see that all of these bridge girders look like they're rusted. The reality is they are. Now, they wouldn't call them rust. They would call it a patina, which is just a fancy word for rust. But essentially, atmospheric steels are nickel containing. And what that allows them to do is to build up a sort of limited scale level of rust that's predictable. So they know that when this steel is left outside, and as long as it's subject to consistent atmospheric conditions, so it's not just having somebody standing there with a hose spraying it, which does happen, essentially you can predict what that thickness of that layer of that patina will be, and it won't corrode past that point, or won't rust past that point. So when we're welding a nickel containing or atmospheric steel, we need to make sure that we are using a nickel containing wire. Otherwise, you're going to have these nice shiny welds that are going to completely fail because they aren't going to be able to keep up with the rust or corrosion rate of the rest of the steel around them. So if you look at the actual code, it will tell you that you only need to meet a F49, which is in KSI, because again, we like to bounce between the two units. But essentially, you only need to meet a certain standard for the actual strength of the wire. But because it's nickel containing and there's limited amounts of products out there in the market, we're actually going to go up one level. So we're not going to go to a matching base to match the base material and strength. We're actually going to overmatch the base material and strength. And this is allowable, and those limits of allowability are defined within the code. But the main thing to take away here is that we're going to match our filler material, with that nickel containing being the highest priority here, to the nickel containing base material. And one of the things I wanted to highlight here, because this is an important thing to talk about when you talk about submerged arc welding, is that we're going to look at the essential variables here. So when we use this wire and flux combination, we choose to use a neutral flux. So I'm sure you guys have talked about neutral versus active fluxes when you talked about subarc welding. But really what we want to do here is have the wire doing the alloying and not our flux, because active fluxes can have very, very good effects in welds. They can also have some fairly negative effects in welds. But more importantly, if we look at the essential variable table for W47.1, what we'll see is that with submerged arc, if we'd like to use any other size of electrode diameter other than the one used for the test, and we use an active flux, we can no longer change that wire size freely. But if you don't use that, and if you use a neutral flux, you can now change that size of wire freely without having to redo the testing, which is an awesome thing. So essentially, if I test it with a 3.2 millimeter wire, and then 2 months I do a project where now I want to use a 4 millimeter wire, I can make that change without having to requalify my procedure. Where if I used an active flux, I would have to redo the entire qualification. So it's again that idea of future proofing by being familiar with the code. So we have our process selected, our essentially our sample. We know what it has to be. We've selected our wire here and our flux combination. The material, this is again one of those things of future proofing, where we're going to select our material. We know that based on this category 3, so this within the Canadian Welding Code, it's defined what that value actually is. So category 3 material needs to meet a CVN requirement of 27 joules, and the sample is going to be tested at minus 30 degrees C. So the sample is brought down to minus 30 degrees C, and then a hit, and they measure that, and it needs to be at least 27 joules. But again, to future-proof, and this is a recent change in the code, and thankfully they've listened. It took a long time of talking and convincing people, but essentially it used to be the case that if you tested at category 3, your weld was good for category 3 only. So essentially, if you went up 10 degrees and you were now welding at minus 20, you had a requirement for minus 20, that welding you did at minus 30 was no longer good, which makes no logical sense, because going up 10 degrees is not going to lose you impact energy. So one of the things that we do within our company is we very often have requirements to go between Cat 3 and Cat 4. So where we're going, Cat 4 is actually an even more intense requirement. So it's minus 45 degrees C. So essentially what we do is we test our welds to category 4. So we test them at minus 45. And by passing minus 45, they made a recent change to the code that allows you to now be good at every temperature range above that to the rest of the categories, right? So essentially back up to ambient room temperature. So it's a really, really good change, because previously it was very annoying and you had to have a bunch of testing to qualify one procedure, or you had to have a bunch of different welding procedures, all good for different temperature ranges. Now, as long as you test in the most severe conditions, you can get the allowance for the other less severe conditions. And that's a very recent change, as that's only in place as of last year. And it took a lot of convincing from industry experts coming to them and saying, look, this doesn't make any sense. If I increase temperature, I am not going to lose impact energy when I break the samples. So it's a good note to know that when you're out in the industry and you see something that doesn't make sense, flag it down. You can reach out and contact them. They won't be happy to hear from you, but you can reach out and contact these people that run the codes to inform them if something doesn't make sense. And if they hear it from enough people, they will make the changes that are required. So it's something to highlight and notice those things throughout codes and standards. So we've selected our material spec for our plates here. We want to test the Cat 4, so that gives us Cat 4, Cat 3, Cat 2, and Cat 1. All of those will be garnered by doing this testing. Now we're going to choose the thickness of our plate. The thicknesses are defined based on the clauses within the code, and I'm not going to go into grave detail here, but just know that it builds in that future proofing. And essentially, by being smart about what sizes of plates you use, you can allow yourself to not have to have issues with what range of thickness you're actually qualified for. So I won't go into the detail of why it's done or how it's done. It's all written in the code, and I'm showing it here. But essentially, if we do the test on an 8mm plate and a 25mm plate, so both meeting the requirements of this test coupon here, the plate that we saw the figure of, if we do it on both of those thicknesses, the 8mm being done in one single pass, well, now we get our welding procedure qualified from 8mm to unlimited thickness. So that means we can weld on a plate that is 8mm thick, a fillet weld. We can fillet weld a plate that is 8mm thick to a plate that is 400mm thick, and we can use the same welding procedure. It's irregardless, just by doing this qualification. So that's a very, very useful thing to understand and use. Now, they're also building this under the understanding that nobody is going to want to apply this to a weld that's that thick. Even when we weld plates that are 100mm thick, people get super uncomfortable because it's very, very difficult to weld at those thicknesses. But it's just to know that you have that power available to you. And by being smart about what you're testing with and looking and reading those clauses carefully, you can build in a very, very wide range of applicability after the fact. The next one up is welding parameters. So what are we aiming for welding parameters? Well, that's going to be dependent on our PQR. So when we actually hand this off to the shop guys and we call on the CWB rep to come witness it, and I go down to the shop floor to witness this testing, whatever the parameters that take place within that test are going to be what is reflected on the weld procedure. But what that means is that when you're welding, talk to your welders. And this is true of any code, any standard, any industry. Talk to your welders and work with your welders. They are very intelligent people and they know their job very, very well. And what you need to do is work with them and get an understanding based on them. You're not, as much as you guys might get out of this course and you have a good welding knowledge, you are not going to be an expert unless you are trained as a welder in welding. So you should work with the people that know what they're doing and find out what works for that process. And if you want to build in a larger range of applicability, you would do that in the PQR. So a good example is this particular PQR where we were welding an 8mm weld, and we have to do that in one pass to meet the requirements of the plates. And then we're welding a 25mm plate, right? Where we're doing a CJP weld there as well. In the 25mm plate, we're doing lots and lots of passes. So this is a good opportunity to build in the lower end of our parameter range. So we're going to build in our lower range by welding maybe a lower heat inputs, going a little bit faster, really building in the efficiency into the process. And then on the 8mm weld, where we have to bake this in one pass, we're going to go super, super hot. And so long as both these plates pass the test at the end of the PQR, what that means is that at the end of the day, we're going to have this very, very wide parameter range that should all meet and give the welders that flexibility. One of the biggest complaints I heard when I first started in my job was talking to welders on the shop floor and them saying, this weld procedure is useless. And I would say, why is it useless? And the guy's like, well, we can't meet the parameters. Like, it's physically impossible. And a lot of the times you have to make sure that your parameters are going to work for them. So use the PQR as a tool as you're doing that. And then the last thing here is the preheat, which is clearly defined within the code. Essentially, you look to this table, it says you have these thicknesses of materials. Okay, you need to preheat to 20 degrees C or whatever it be for your material and your thicknesses. So at the end of the day, we're going to create these two plates. We're going to essentially need to have the CWB rep there to visually witness the testing and record all the parameters because they don't trust you to do it. And then you're going to take those samples, cut them up, and you're going to send them off to the lab, get the CVN testing done. And at the end of the day, you'll have your completed welding procedure that is good for the following things listed here. And the biggest thing that I want to highlight, and I put in a new requirement that's been added in, I didn't want to build it into the actual case study here because I think it just adds confusion, but just for completeness and for accuracy, I wanted to build in that new requirement. But really the big thing I want to highlight out of this case study is when you build your weld procedures and you're going through this PQR process, use the code to your advantage. Build in the flexibility that you need moving forward. Like I said, one welding procedure, so one $8,000 cost. Yeah, we ate that $8,000 cost up front, but now moving forward onto future projects, we get to advertise that awesome welding procedure and use it to our competitive advantage to say, look, we can nail this 100% of the time because we put in the work properly to make a good welding procedure and to make a reusable welding procedure that gave us the flexibility we wanted down the line. And that's really, the code can be an impedance in your job and it can be a headache sometimes, but it is also a very, very powerful tool to help you out when you're building welding procedures. And that's true regardless of the field you're in. So the specific example I've given here today is specific to the structural field, but those lessons are true across all of the different industries. And then the last thing I just want to touch on here before I show you the actual welding procedure we got here, we have just a couple minutes here, is I just wanted to mention quickly the AWS structural codes. The reason that I mentioned this is the AWS, and I'm sure Eddie could attest to this if he's worked on some of these jobs, is AWS is a little bit like the Wild West. So as involved as the CWB is in the structural side for the Canadian market, AWS is just as uninvolved. So for welder testing in Canada, for example, when you do a welder test, the welder has one chance to do it. If he fails, he has another chance to do it. Well, he fails that, now he has to go back and do training and prove that maybe there's some things he needs to learn. In the AWS, everything is self-administered. So that means that I create the welding procedures, nobody reviews them, the client will review them, but they probably don't know what they're looking at. So all those things are self-administered, including welder testing. So if we certify welders all the time for AWS jobs, and essentially the methodology is more or less, here's these 20 samples, I hope you can pass one of them. Because that's all you need to do. You don't need to have any kind of repeatability. You just need to be able to pass one. So one of these things I like to mention this because a lot of that accountability ends up on the plate of the people who are supervising. So be it the certified welding inspector or the engineer signing off on the procedures. A lot of that accountability to make sure things are being carried out properly is on them because there's no third party stepping in to say, hey, wait a minute, this doesn't make sense. Specific owners might do that, but it's fairly rare because not a lot of them understand the code well enough to do that. So it's just one of those cautionary points I like to point out there for the American code that you need to be aware of. So like I said, that's going to wrap up our presentation. I'm going to quickly jump out here and show the welding procedure of relevance here. So this welding procedure is the welding procedure that we designed here. So you can see all the relevant things here. It's sub-arc. It has the material ranges that we qualified to. It has the consumable that we qualified it to. It has the different materials that are qualified. I said the group 1, 2, 3 is there. And it has the notch toughness requirement. So here, like I said, this is actually an old version of this that I pulled. I didn't realize that, but our current one says qualified to minus 45 degrees C. And then it has all the welding parameters here listed. Nicely in the Canadian and American systems, you're required to show your welding parameters in SI units. And the American codes are also written in SI units. So it's one of those things that is very, very important to note, is that SI units is the universal thing, but people in general, when they're talking in industry, are going to very often talk in imperial units or a mix thereof. So try to get as familiar as you can. If you end up working in a field where you're building welding procedures, try to get familiar and essentially bilingual in those two systems, because otherwise you're going to get burnt at some point by somebody mentioning something and it gets confused. And you just need to make sure you're very, very clear about what things are listed in, particularly heat input, because the difference between kilojoules per inch and kilojoules per millimeter is quite large and makes a huge, huge difference. You're talking in the 40s versus in the 1, 2, 3 kind of range. So that's just something I wanted to highlight, and I'll pass this welding procedure along with the presentation slides as well. So you guys have that as a reference point if you're looking through that case study to be able to glean some of that information. I know it all went very, very quickly, so I didn't want to blow through it too much, but it's just the requirements of the time, right? So if you want to look back at that, you're more than welcome to. So if you guys have any questions, I'd be more than happy to answer them. I see we're right at 3:20, so I mean, I didn't leave a lot of times for questions, so good for me, I guess. But if you have any questions, I'm more than happy to answer them.
Thank you, Nairn. This is awesome. Thank you. You guys are quite lucky to be in this city and coming to this university. The fact that we have access to people like Nairn today, or we had access to Eric Shervy last Thursday, it's amazing. So if any question comes up, I can forward those to Nairn, and I would suggest we stop here so everybody gets ready for the quiz. Thank you again, Nairn. Many, many thanks.
Yeah, not a problem. Good luck in your quiz, guys.
All right. Thanks. Until next year at the latest.
Happy to help. And if you guys have questions, like I said, feel free to forward them to Patricio, or you can reach out to my work email as well. It's my first name dot my last name at supremesteel.com. I'm always more than willing to help out with code questions. Like I said, if you're working in a pipeline or plant industry, I mean, I don't know how much help I'm going to be, but I could point you in the right direction.